So the outline for today's lecture, I'll just do a brief background and motivation for why this lecture is important, and then I'll describe the two main types of data. So we have our thermodata and our kinetics data. So let's get started with some background. So the scope of all possible reactions that might be relevant to your system is usually very enormous. And so RMG models commonly have hundreds, maybe thousands of species, and they could have tens of thousands of reactions. And so in a perfect world, we would turn to the literature and we would obtain reliable values for every single species and reaction. But currently, that's not usually possible. So things like NIST or CCC-DBD don't have, like hundreds of thousands of entries that we would be using. So instead, RMG will use some simple data-driven estimator to quickly predict the values that are going to go into your mechanism. And just to give an example, so this slide shows the distribution of values that came from literature versus those that came from being estimated by RMG. I believe this slide was designed by Max many years ago. He was a former PhD student, and it was just for one of his methane oxidation mechanisms. And the main idea is that the mechanism has hundreds of species in the core, and it's approaching 10,000 reactions. And many of these values are estimated, especially so for the edge. So where do all of those estimates come from? The video yesterday from Matt Johnson covered this in more detail, so I'll just give a very brief summary today. So the thermal values are estimated using group additivity, though we are in the process of trying to evolve that to a decision tree, which was mentioned yesterday. It's a work in progress. And then the kinetic values are estimated using decision trees, and we'll sometimes call those rate trees, just more colloquially. So these estimators are trained on data. So where does all of that data come from? So ideally, it would be our goal to have all of those values in RMG database come from really reliable sources, and that could be either experimental results or accurate quantum chemistry, and they could have gone through peer review. Currently, it's not quite the case. So just as an example, a lot of kinetic entries in RMG that are used to train the rate trees are actually themselves from a group additivity estimate. But we are always trying to improve RMG database, and I wanted to briefly highlight, I guess, like some success stories that we've had on that. So just as one example, these two papers on the left did some really good quantum chemistry calculations. And after the results of those calculations were integrated into RMG database, we had some very reliable values for the species thermochemistry, as well as the rate coefficients for some phenyl migration reactions. And those values ended up being very helpful when constructing this pretty large kinetic mechanism about pyrolysis. So feel free to check out those papers for additional detail. But we don't just, create or calculate reactions for specific mechanisms. We also just proactively work to improve RMG database in general. And so our group actively is working on creating many high quality data sets with the goal of integrating them into RMG database, just so that everyone's mechanism generation process goes a lot more smoothly. And so one example is this paper here on the left that I published with 12,000 reactions that were calculated at explicitly correlated couple cluster, CCSDT-F12. If those letters don't really mean anything to you, that's okay. The point is just that it's basically the most accurate level of theory that you can use to calculate something. And their values are often within a kcal of experimental values, so it's very accurate. And I've integrated many of those reactions into RMG database to improve the experience for everyone. So again, feel free to check out those papers for more detail. So just to summarize the background section, we will gladly incorporate experimental data when it's available, but more commonly, we rely on various electronic structure calculations that are then passed to transition state theory to calculate rate coefficients that are then integrated into RMG database, that are then used to create detailed kinetic models of elementary reactions using RMG. And then you can simulate the time evolution of those mechanisms with your favorite software. So the focus of today's lecture is how to integrate those values into RMG. So by the end of today's session, you should be able to describe the different data sources that exist within RMG. You should be able to add new species thermal data and libraries to RMG database. You should hopefully learn how to add new trained reactions and possibly kinetic families as well. It's a bit more complicated, but we'll talk about that today. And then run an RMG job with the updated database. That way you can benefit from having those additional values in your mechanism. So the next thing I'd like to talk about is the data sources that exist within RMG. So these are kind of summarized with our list here on the left. So we have both thermochemistry and kinetics. And so within the thermochemistry, we have libraries, groups, QMTP, which stands for the Quantum Mechanics Thermodynamic Property Interface. And that allows RMG to determine on the fly quantum chemistry calculations. And then finally, we have an ML estimator. And I believe, again, Matt Johnson's video from yesterday went into more detail on each of these. So I'll stay more like high level today. So there's two important properties of these. And, the first is like, how easy is it to add data to RMG database? And then the second is whether doing so will improve estimates, for many other species and reactions, or just for that one species and reaction that you added. So we'll discuss the different cases here. So just starting with this first column, which is the ease of adding data. So it's relatively easy to add new entries to an existing thermal library. So you just follow the format and the syntax that is already present in that library. Adding new thermal groups is a bit more complicated. Hopefully it will be easier once we convert to a decision tree approach, but that's a work in progress. And then QMTP uses Mopac, which is a third-party software. So we can't add data to that or change their third-party software. And I think actually it was basically deprecated until last week when Jackson revived it. So shout out to Jackson. And then our ML estimator is probably, I guess, the hardest to add data for, simply because it requires knowledge of like software packages that are kind of orthogonal to working with RMG. So if you happen to be familiar with those packages, then it shouldn't be too hard, but we'll label it as more challenging for now. And then the other important characteristic is whether adding this new data will improve other estimates within RMG. So for the libraries, if you just add one species to that library, it will only help that individual species. But in contrast, if we were to add a new group or update the value for an existing group, then that will change the thermal estimate for any species that contains that thermal group. For QMTP, its job would be to calculate, the value of one species, so it would just impact that one species. And then if we were to upload new weights for the ML estimator, then that would, impact the predictions of everything that ML estimator is used for.
Question about the machine learning. If you just want to use the estimates, but don't want to like add new data, do you have to like install PyTorch and do all of that stuff, or is it like just the development side that requires all that like extra know-how?
I think he would have to install it. It's not super actively used, but I can look into that and try to follow up with you.
I think currently RMG managed to with PyTorch and stuff. And so if you just in the RMG amplifier just turn on saying that to estimate like range species with machine learning package, it should be able to do that automatically. But I think we need to test it.
I don't remember if it's in the YAML file, but it's been a while since I've looked at it. So yeah.
So like the estimators that we've already programmed in there are included by default. But if you want to develop new ones, you probably would need to add some additional stuff. But yeah, we'll follow up with you separately.
I think you answered the question.
Okay.
Thanks.
Yeah, and thanks for helping to answer. So on the kinetic side of things, we have libraries and families. So like before, the libraries are relatively easy to change, but they will only impact that one specific reaction. And then for the families, adding new nodes to the rate trees used to be pretty difficult, but thanks to a lot of hard work from Matt, this is now, I would say, a lot easier. So we'll call it medium for now. And doing so will end up improving the estimates for all of the other reactions. So for the next portion of this talk, I'll just kind of go into more details on every single one of these boxes on the left. So this is the format and syntax for what RMG's thermo libraries look like. So on the top, we have the library name. So that's our header right here. It's the primary thermal library for this example. And this name should always match the file name. So somewhere in RMG, you'll have a primary thermal library.py, and I'll show that coming up. And then that's going to be followed by all of the different entries for each species. So for each species, we're going to have an index. Typically, it starts from 1 and just counts up. So it acts as a unique identifier. And then we'll have a label, so H2. And then we'll also have, molecular structure. So in this case, it's the adjacency list, and then an entry of the thermal data. So just regarding some logistics, all of our thermal libraries are going to be located at this file path. So we're going to have RMG database, input, thermo, libraries, and then in that we'll have a lot of Python files that are storing the thermal libraries. And just to help give an example of where you would find this, if we go onto GitHub and we look at the source code, we see RMG database, input, thermo, libraries, and then we see a snippet of some of the libraries that exist within RMG. So the thermo groups have a similar structure and syntax as the thermal libraries. So we start off, with a header at the top, and then we have, our index group structure and corresponding thermo. And then regarding the logistics, so this is just the location where we would find those files. We have RMG database, input, thermo, and then this time it's groups. So the top part of the file path is the same. And then again, everything is going to be a single Python syntax file. And if you need help visualizing like what those groups look like, this tool on our website should be helpful. So you go to RMG tools and then draw a functional group, and you could copy paste the adjacency list, and then it would try to draw it out for you.
Kevin, what do CBF and CB mean? You're in that group drawing?
Yeah.
Like the capital Bs?
So I believe that's carbon benzene, but yeah.
Yeah, it's benzene. It's carbon atoms that's in the benzene ring. So you can see CBF is fused benzene ring. So like the polycyclic, like a pH structure. Those because they kind of and B is benzene bond. Because instead of treating it as single and double bond separately, treating it as benzene bond will help you improve the thermal estimation, so that like for benzene ring you should apply this kind of group and values instead of using a single and double bond structure.
And do you know where all of that is documented? Is that just in the RMG documentation?
I think
It should be.
Yeah.
Okay.
Yeah. But feel free to ask us questions. That's the point of the training. So thank you. Okay, cool. And then there's a few different categories of groups that are used to make the thermal estimate. So we have, our base group, but then there's separate groups for radicals, rings, polycyclic, et cetera. So, you can find more information in those files in the source code. And then this is would be the file path to the ML estimator. And so like we kind of said before, if you wanted to add new data, you would have to retrain the model to incorporate that data into the model weights. So probably contact us if you're interested in doing that type of approach. So now we'll transition and look into kinetics. So similar to the thermo, we have libraries for all of our kinetic reactions, and it's a very similar syntax where we have a name at the top. In this case, it should match the directory name, not the file name. The file name is going to be fixed as reactions.py. And then again, we have an index. Typically, it starts from 1. It's just a unique identifier, and it will count up. We'll have a label for the reaction, just so it's human readable and we know kind of what this is doing. And then we have Arrhenius data that could come from either experiment or a quantum chemistry calculation. And right, yeah, the next thing I want to show is just that this label is going to be important. So I'll talk about that on the next slide. So all kinetics libraries need 2 files in the same directory. The first is the reactions.py from the previous slide. And then the second one is this species dictionary that is used to define the molecular structure for everything that's participating in the reaction. And this is important because it's going to define the connectivity, the charge, the multiplicity, et cetera, so that RMG knows how to represent this and what exact species is taking place. So this is where we would map, the label on the previous slide, H or H2, whatever, back to this dictionary.txt so it knows exactly what it is. And sometimes species might have different multiplicities, and in this file is where you would specify that so RMG knows how to represent it. Regarding logistics, all of the kinetic libraries are located here. So RMG database input, so this time kinetics rather than thermo, and then libraries. And again, everything is a Python syntax file. And then the species dictionary is just a plain .txt file. So this is what it would look like if you would go to GitHub and try to look at the source code. input kinetics libraries, and this is a list of folders. We have many more. This is just the top screenshot. And you could look into there for more detail. So then last thing we'll do is we'll talk about kinetic families. So we want to use rate rules to estimate kinetic parameters for new reactions that are not already in, I guess, the training set. So the header is going to be a bit longer just because we have to define groups that are going to like define the reaction template that is occurring in RMG. And then same thing, kind of like before, we have many different entries, just counting up, and then kind of like we say here, the adjacency lists will have labeled atoms that are corresponding to the reaction recipes. Those are going to be like the starred entries. There's going to be another file that's called rules.py. The header is going to be the reaction family that we're looking at, and then /rules. So this example, it's the R addition multiple bond template /rules. And then we're going to be having a label, each group for which the rule is applying for, and then each entry is going to be a rate rule. So historically, people would do this by hand, but we're going to have an automated notebook that'll show today that will generate this for you.
Where's the template?
For the template, that's going to be defined in groups for like the recipe. That's what you're asking, right? Yeah. So
every time you add a template there, you also have to add that other file that has the rate estimate for that template.
You have a file generated
yeah,
automatically, but you might need to create a blank file. Just like
the blank root node, I think, is what you have to do. Yeah.
The
Yeah.
blank root node would be in groups.py file. I think the
Yes.
real file will be completely regenerated.
I think that's correct.
I'm sorry, now I'm just even more confused. Okay, so the template's here.
Yes.
That final thing you showed us, other file, that has all the rate estimates, but somewhere else in between is a more specification of the tree, or that's all done automatically.
The tree would be the bottom of the groups.
Yeah.
It will show like the complete tree structure.
And usually you would have to edit that, or is that all?
No, it will be generated.
Yeah.
Okay, so you guys don't have to touch it, so somebody.
Yeah, the minimal thing you need to define a new tree is kind of what Kevin just said, like the name, the template, the recipe, and whether it's reversible.
Yeah.
And the top node. So everything here is the bare minimum you need.
So I'm still confused that, how does the computer know when you make the other file with the rate estimate? Or is the computer generating that file also?
So rules should be generated automatically, which I think is what Highway is saying. And it's generated automatically from that notebook that Matt had contributed, and I'll be going through an example.
Yeah, I guess
today.
you have to make a rules.py file with a header.
Yeah.
Okay.
But all the rest of the entries will be generated.
Yeah.
And somewhere it's generated a tree and saying exactly which functional groups are nearby the place where the reaction is occurring that correspond to this particular root.
So the entries in the rules.py will share the same label as the groups.py. So whatever group that it generates will have a corresponding rule here.
Okay.
Yes.
And then the numbers here would normally be computed automatically by RMG from your training there.
Yeah, it will
Yes.
from averaging. So like, okay, the script generated tree structure and the data got distributed on the tree structure. And it will start averaging from the bottom.
So all these things here, you would not edit really, except if you're adding a new continuing reaction template, you would edit that.
Yeah.
But the rest of this would all be auto generated.
Mhm.
Yeah. What?
And you're gonna show them how to add the training data.
Right. Yeah. The main thing that you guys will probably be adding is new training reactions for existing families. Adding new families is a bit more complicated, and you probably want to collaborate with us, which is kind of like what this discussion is trying to clarify. So yeah, I'll give examples of how to add new training reactions.
But you might want to read this, because here you can see what the actual estimate for RMG is using.
Yes. Yes.
Where it's really coming in. So sometimes you okay, you might be confused why RMG is using some number.
Yeah, but when the RMG generate like a 10K annotated file, that it gets that you can submit, there's a same into file that I don't open. So at each reaction, there will be a comment from which node the estimate came
Yes.
from. So you can look at that node name, you can go to this two file and see what is the structure, what is the rule that we get here. And how many data is average could be also in a
I guess any other questions before wrapping up the slide deck? Okay. Yeah, I think we covered that. So I think just the last couple slides here, just for the logistics, if you wanted to look at where the families are, this is the path for that. And then it's always going to have, again, just Python syntax files. Right. Yeah. So historically, many years ago, people would manually change the rate rules, but instead your job will be to add new training reactions, and then that will be passed to an automated script that I will show today. And that script, I guess, just for your information, you could add a kinetics library to RMG database, and then you could pull this notebook from RMG IPython, and its job is to convert the library into training reactions, which will then get passed to notebook number 2, which will refit the rate tree. So I'll show that now. Yeah, and then I guess, yeah, last point is just if you wanted to look at where the training reactions are, they'll always be at this type of file structure where you have input kinetics families and then family names like B Diels-Alder, H abstraction, etc. Any of the supported families in RMG, and then training. And then you'll see a list of the training reactions that are used to fit the rate tree that will then go on to make all of the estimates when generating your mechanism. So that's the end of that slide deck. So now what we want to do is here.
Do we have anything open, Kevin, or just what we're doing?
I think just watch for now. Yeah. Let's see.
But then later will we get a chance to?
Yes. So at the high level, so I'm going to walk through one example today, and then I'll have Shara email out another example with kind of a worksheet, and you can go through that, on your own time. It will cover the same steps that I'm going through today, but I figure a live demo and then follow up in your own time is a good way to try to learn. So the purpose of this notebook is we're just going to identify some reactions to add to RMG database. So I guess the main idea for this is we're going to go back in time like 9 months ago when I had published this paper and I have lots of high quality data. We want to start adding some of that to RMG. So I put my Git branch back in time before I had added the data, because currently the data is in there, and we're going to walk through the process of how I ended up adding that data. So just first things to do, I like pre-ran these cells, but so this data set has nearly 12,000. That's a lot. We're not going to go through all of that today. Instead, let's just pick something that's like very tangible. We're going to look at Diels-Alder reactions, and as it turns out, there's only 3 of those in this enormous data set. So that's going to be a nice thing for us to manage in this example. So then the next piece of code that I have is just trying to figure out if any of these are already in RMG database, because if they are, maybe we have better values, or maybe the value that's there is already good enough and we don't need to add it. So that's just kind of the first check that we want to do. So I'll kind of, skip over the code. We can send that later. Conceptually, the very first example we have is just our very classic Diels-Alder reaction where we have butadiene, ethene to produce cyclohexene. As it turns out, every single item in this reaction is already in RMG database. So this reaction is already there, but as I'll show later, it's not, I guess, a good estimate. So we'll be updating that to make RMG database better. For the other 2 reactions, just to see what they look like. So P-0, that's just saying that ethene is already present, but the rest of them are not. So this will be a new reaction that we're adding. And then for this third reaction, we have P-1, so butadiene already exists, but that's okay. The rest of these don't. So this will be like a second new reaction that we'll be adding. And just to summarize, so these 2 reactions do not exist. So those are going to be great additions. For this other one, it's already a training reaction. However, it was converted to a training reaction from a rate rule. So it's not from like a high quality transition state theory calculation. So it'll be really beneficial to update that value and make it more accurate. And let's see here. So just to show what this looks like, so this is what the reactions.py file looks like before we've added any data. And here we see for that very first training reaction, we have our ethene or butadiene to produce our cyclohexene. And we see in the comment that it was converted to a training reaction from a rate rule. So this is the one that we want to replace. So then the other thing that's important to point out is the rank. So I guess I went kind of fast on the reactions.py file, but each entry in the training set is going to have a rank that is used when making the decision tree in terms of what priority it should be given. And if you did have multiple entries, which one like it should overwrite. And so for the one that was already existing, it was rank 11, which is, the average of multiple rates. And then the ones that we're going to be adding were calculated with C60TF12 with a double zeta basis set, and we did 1D Hendrick rotors. So we're going to call that as rank 4. So then the next step is we want to take those 3 reactions and make them become a train or become a reaction library. So you could just follow the existing syntax of one of those libraries. And let's see if I can pull this up. So this is what the library will look like. So we have those 3 reactions in the notebook. And so here, this folder is just going to have 3 different entries. And these entries come directly from an Arcane calculation. So when we did all the quantum chemistry calculations, we passed it to Arcane, which is another software within RMG, and it produces these outputs. And when it's just 3, we can copy paste them in there. If you had hundreds, you could write a little script that just programmatically copy pastes over the lines. But the point is that we will end up with this reactions.py file, and we try to add, very detailed comments so that in case anything goes wrong, people know who to come back and ask questions to. So here we have 1, 2, 3 reactions that we will then be adding to RMG. So once we have that library, we now have to convert it into trained reactions. And to do that, I'll be using this notebook. And this notebook, get the zoom bar away. This notebook is located in RMG.py, IPython, and then we're going to take a kinetics library and we're going to convert it to training reactions. So that's the purpose of this library. And so if we run this, right, sorry. So then the other, detour to bring up here is what thermal libraries are going to be used. So when we're making the rate trees, RMG will use the thermo to estimate the reverse rate, and it will use both the forward reaction and the reverse reaction when creating the rate tree. Now, if you don't define a thermal library, it will use group additivity to estimate the thermo. But in this case, because I've already done the quantum chemistry calculations, I have the thermo for these reactions. So I created a thermal library that will then, I'm letting it know that that exists so that it has more accurate values when calculating the reverse rate.
In choosing the thermal libraries, do you have to make sure that they match the presumably for your calculations you use the because Arcane requires the thermo in order to do the kinetics, right? Do you have to match the basically the thermal library, like the thermal calculations that you did? Do you have to make sure that those match the ones that you're putting in now for the kinetics?
Yes, you would want to. And so for this example, because everything is coming from the same database that I created and calculated, everything is consistently the same level of theory. And what's contained in this file is just individual thermal entries for each of the species that are participating in the reaction. And it will use those to calculate, enthalpies and then calculate the reverse rate. So just walking through this notebook, it's on the RMG website. So just kind of giving an example, and it will give a nice, visualization of how the reaction that you're adding is different from what the current estimate is. So for this first example, it was actually already a training reaction, but we see that the new estimate is substantially faster, and we're looking at, many orders of magnitude different. So it's, a lot better that we add this reaction than use the old estimate. And for this other reaction, there was no exact trained reaction to query from. Instead, it was using the rate tree to estimate the rate. But again, same thing, that estimate was too slow, and that's not good, because then maybe RMG would think, oh, this reaction's not important for your mechanism, but if it's actually several orders faster, then maybe it is. And just another example, the third one, again, the new rate, calculated rate is faster than the previous estimate. And then this next step in the notebook, it will kind of prompt you to manually review things just because we want to be really sure about what is going into our RMG database. And that ultimately requires, manual kinetics experts to look at these reactions and know what's going on. So it will just prompt you with, do we want to add this reaction? Do these values look correct? Are they actually what came out of the arcane input output file? And I've done this before, so I will say yes. And same thing for these three. So we'll just manually type Y 3 times. Yeah, this is just seeing if there was any like multiple matches, but that's not flagged here. And then it just, to be extra safe, it will print these out again, prompting you to please look at it and please be very sure about what you're going to put into RMG database, because it can be kind of a pain to undo. And then we will write all of these new training reactions to the database. So it previously had 19, we now added 3, and we can now use this updated set to retrain the rate tree.
Where are the previous 19? I thought there was just the one that matched what we already had.
So that's the one that matches, but there were, I guess, 18 other ones. So the total list of deals, all the trained reactions was 19, and we now added 3 more. There is a subtle thing here where I don't know if it actually overrode the existing one. So I did have to delete it and replace it, but that's, I think a pretty specific case. So now we have that new training reaction. So then we pull up this second notebook, and this notebook is located in RMG database. So you can go and run it here. I'm just choosing to run it on one of our servers. But the point is that now that we have the new training reactions, we want to refit the rate trees. So let's see if this will run. Cool. And so, I'm specifying the reaction family as Diels-Alder. I don't need to load everything else from RMG database, just the thing that I'm interested in. For the thermo libraries, I'm going to give the highest priority to the thermo for the exact species that are happening in these reactions that I calculated. But for everything else that's in the training reactions that I didn't add, we want to have thermo estimates for them that come from somewhere. And so there we have listing other thermal libraries.
If there's overlaps in those libraries, the one library system first is squared.
Yes, that's correct. Yeah.
Yes,
So
this is a common situation. You might have the same molecule in many different libraries and all the different numbers for what the thermo is. And so you need to use one number. So put the library you trust the most at the beginning.
Yeah, Bill has a great point. And I guess through years of experience, other people in the group have kind of suggested that this is a pretty good order, but I think that's listed somewhere in the RMG database documentation. So then we just kind of walk through this notebook. So we'll kind of erase the existing rate tree, and then we will start to generate a new one. And it will take a tiny bit of time, but because there's only like order 20 training reactions, this will go pretty fast. And yeah, it's already done.
So you got an error 22.0.
It's not actually an error, it's telling you there are 22 reactions, but it's for some reason it gets sent out as error
Yeah.
message, but
Okay.
it's actually just like information.
And so the rest of this notebook is just kind of walking through, we have our different templates. We're going to erase the rate rules. So we made like new groups, but now we have to add like new rate rules to all of that. And then these are kind of the error values of what the decision tree is predicting versus what the true training reaction value was. And this will just give, the distribution of the estimated divided by the actual. And then we see like kind of what the median absolute error in our rate constant is, what the mean is. And then the last line is the, I guess, important one that will then save this updated tree to, and it will overwrite the files. So at this stage, and now if we were to go into GitHub and do a little git status, we see that our groups, our rules were changed. So that's what that notebook just did, or maybe that's too small, sorry. the training reactions, the dictionary and the reactions, those are the ones that we added manually. And then I also modified, my thermal library for this specific example. But the main thing that you'll see is that these first two are different because that notebook refit the tree and then overwrote the existing values. And at that point, you would just push these changes to GitHub, make a PR, and now you have contributed to making RMG database better.
When you have to run the one that are more reliable to you resources,
Yes.
if you have one source that is more reliable for one particular temperature conditions and you have another that is more reliable for other, do you run as a general or you can specify like the changes that are like that you have more like more reliable information?
Okay. I mean, you're welcome to add entries that are valid for multiple temperature ranges. The rank that's most important is decided like from this table, and then that's decided by level of theory, not necessarily by temperature range. I guess, does that like make sense, or am I answering your question?
And data, for example, for quantum chemistry for a particular conditions, and you have, for example, experimental data from
Yes.
a particular condition that you are doing once. So
Okay. Okay. Yeah, so I think that's kind of one of the benefits of using the calculated data, because when you pass it to Arcane, you can ask it to calculate a rate coefficient, ranging from 300 to 2000, and then fit the Arrhenius expression over that entire range of temperatures, so that it will be valid, like a more valid training reaction when making the predictions. The experimental stuff, yeah, if people only measured it for a narrow range, if it is then used to fit a rate rule that is then making predictions outside of the temperature range, there might be some loss in accuracy. And that's why, as Howie brought up earlier, in the ChemCam file, it will always say exactly what node in the rate tree this estimate comes from. And if sensitivity analysis shows that reaction is causing you issues, then you can kind of eventually trace that back to maybe this temperature range wasn't valid.
Yeah, I think in RMG, we generally treat experimental data as very high rank. Yeah, rank 1, which is there isn't like very detailed ranking on how good quality the experimental data is currently. But when you add experimental data, you should always comment on what experiments you did and what's the error bar, and like try to be more specific about in what temperature range that you fit to. Like try to be more specific about that, so that those will be included into the generated model. It will have a comment section to spell that out. That's the current way. Yeah.
Something to be careful about is that for high temperature reactions, most of the reactions would be pressure dependent for guesses. And so the experimental numbers you get will depend on what pressure was used in the experiment. And it would be easy for RMG to mistakenly use that number at some wildly different pressure, in which case it could be way off. So there's like a lot of, it's quite tricky that experiment numbers are usually better close to the condition where they're measured than any calculation, but you just widely load up the whole database full of numbers. It's easy to confuse RMG. And there's some special ways to try to handle this by taking your experimental data and like doing a fitting procedure to try to refit it to get hypershell interface. That would be the kind of RMG.
So I think that covers everything that I was going to present on. I'll just quickly check my notes, but also now is a good time to ask any additional questions that you may have.
Your error was up to like 9. Is that like 9 speaker mean units? What's the units on that error?
They're 9.
Is that good?
They're like 9 Matt Johnson units. No. It's what are those log? No, what are they?
I think there's like some log scale fitting at the standard deviation. Like
Yeah.
they took the log scale on the rate coefficient at like 1000 Kelvin.
Right, yes,
temperature, and then
thank
they report the 2 times the standard deviation. There's some math formula that
So I guess what's a good number then? Like what error? Like at what point would you be like, oh, it didn't fit very well, I shouldn't use this?
I feel like empirically, like above 10 is maybe a little bit suspicious, and often for the families that I've worked with, like 3 to 8 is usually what I see. And often once I've added my new training reactions, it like will decrease the standard error because it's had more examples to train on, and also the examples that I'm adding are pretty high quality. So like it's fitting to the truth, whereas some of the other examples that were in the previous training reactions were maybe far from the truth because they were just estimated. So yeah, I'd have to double check, I guess, the documentation or look at what Matt Johnson was doing to see how exactly we got that number.
Okay.
Apologies for that. But that's kind of a rough rule. Yeah.
Yeah, very, very important comment is that the errors in estimates can be pretty large sometimes. Quite large. Like many orders of magnitude. Sometimes it's okay. But it's if you're an experimentalist who worked hard to measure a rate constant to within 50%, you might be quite alarmed when you see how gigantic some of the errors are.
Yeah.
Um,
So like,
yeah, there we go.
yeah, this is just like, I guess, an example to build off of what Bill was saying. And I think maybe I'm not sharing my screen, so apologies for the people on Zoom. So just to build off of what Bill was saying, this is an example where the new is the calculated training reaction that I am adding. The current is like the previous estimate that the rate tree was giving. And we can see how in this case, the units are very clear and we are several log units away. So
And is this log 10 or log?
it's probably log 10. Yeah.
Wow, so that's a lot. Right? So
Yeah. So yeah, so adding these new training reactions were very helpful for the deal solver rate tree and for all of the other rate trees that you know I've kind of been adding data to over the past like year.
And this actually is a great illustration too. You can see how the two curves are at the high temperature limit, the left-hand side, they're converging. And so often at high temperatures, you don't have such a big problem.
Yeah.
But a lot of numbers will agree pretty well. A lot of different estimates will agree pretty well because it's mostly just the A factor. And people can estimate the A factor pretty well. And the challenge really a lot is the barrier heights. And that's the different slopes of the range plots. And then at low temperature, it makes gigantic errors. You can see the far right is like room temperature.
Yeah.
And that's, you know, who knows what that is. Well, I trust Kevin's calculations. This limit must be perfect.
It's probably pretty close. But yes, in general, yeah, Bill's statement is very valid. So low temperatures are always trickier. And that's, I think, kind of also speaking to Kariana's point earlier, where if I add a training reaction to RMG, I can ask Arcane to calculate it from 300 to 2000. So we have like pretty good Arrhenius fit over the whole temperature range. Sometimes experiments will report values for say 500 to 1000, and you don't really know if the value is going to hold well at 300. So, you know, RMG does the best it can. Any other questions before I relinquish the floor?
Are there questions about above? You have like those two really long circles with a lot of letters in them.
This is
that something interpretable, or is that just ignored?
in my opinion, no, but it's machine interpretable because this is how the
Well, I don't know.
nodes.
If they are plotted separately, if you can see exactly what I said, it's saying that anything that's
I mean, you have C double, like CO, C,
like
like,
nitrogen with
yeah.
like 5 balance and triple bound and CO double bound, and like this is a plotting problem moment, but it's basically
It's how the function is being classified. What being lumped
Yeah.
together as similar.
so now it will accept anything that
Like a
has
double
this
bond.
kind of this kind of
yeah. So
structure.
based on the training reactions, the nodes on the decision tree are looking for certain groups, and as you go down the decision tree, it gets more and more specific. And so at the higher levels, the nodes are more general, they will match like more groups basically, or more reactions. So like that is what this is doing. It's machine interpretable. Yeah.
Thank you.
Yeah, actually, maybe I asked a question. So this is a nice explanation of how you do the rates.
Yes.
For thermal, do we have an automatic refritter or we have a refritter? What's the status?
We have a group refrigerator right now on the web, in the, there's a notebook that you can fit groups automatically. You can find it on I guess you can find it in a Docker as well. I think it's in the IPython folder. But for really feeding the whole tree, I'm still working on getting the code in. Yeah.
So, yeah, maybe just a comment about fitting. So the, one thing of kite fitting you'll do is fit like experimental data points or quantum points to Arrhenius forms and stuff like that. That fitting almost always works great. And if you get something fitting out of there, something really crazy bad happens. But most commonly it's fine. But the next level fitting, like if you're trying to fit thermo groups show up in a lot of molecules. You need to find a set of thermo groups that's consistent with all of the molecules for training set to try to predict the thermo of all of them. And we want thermo to be super accurate. So it needs to match them all really accurately. Now, unless you take special care, typically this is like a large scale linear regression. And what you'll end up is that your set of training molecules will not have good coverage for certain linear combinations of the groups. So some of the linear combination groups will not be well determined by your fitting procedure. And so many of the functional groups will be well defined, but there'll be certain linear combinations that you just don't have enough data of diverse enough type molecules to be able to specify them very well. And this is like a famous problem, at least for in linear fitting. If you have a linear regression and too many things you're fitting to, it's hard to have data that really conclusively fixes all of the numbers. So this is the problem you're probably familiar with, but just be aware this will come up a lot if you do group refitting, that you'll get all the group values that'll fit, they'll give you something, but they might give nonsense results for certain groups are not well determined, which if they're not determined, that means if you hit a molecule that hits that linear combination, you can't trust the prediction of the group contribution. But the reason why that happened was you didn't have any molecules like that, or not very many molecules like that in your data set. So maybe your next molecule won't be messed up either, and it might be fine. So just because your predictor predicts a bunch of numbers correctly for a lot of molecules, you might be okay, but the next molecule might be the one that hits the bad spot. All right, now that's for the linear fitting. If you're doing the trees, it's slightly better. It's done in a way that's less likely to have like these linear combination problems, so you can still have big gaps in the trees. And so Kevin's example there shown from the kinetics shows like there must have been a huge gap. The program is just randomly guessing what the rate constant is. When he actually put a real data in, it wildly changed the predictions.
Yeah.
Because he filled the gap and he made it more specific. And so it's a little bit more transparent, I think, in the tree case, where you can see that there's a whole lot of reactions all being classified together to one node of the tree. And if you look at them as a human, you say, wow, these molecule reactions are really not that similar. So why is it estimating them all the same? And that's really because you didn't provide enough data, so they had no idea. So it says, well, let's just lump all the ones that are triple bond all together, whether it's a C double triple bond N or a C triple bond C, we'll just say they're all the same because we only have one triple bond example in our training set. So you'll have the same kind of issues, however you do it. And you did machine learning to fit it, you still have the same kind of issue. Basically, you don't have enough data information. You just don't have enough information. And that's why it's very important to learn how to add new data to the training so that RMG can get better and give estimates for those types of molecules and reactions that we don't have any coverage for. And this is going to be like this forever because chemistry is really, really big and there's always some wacko new reaction or functional group combination that you may not have seen before.
Yeah. Thanks for that, Bill. And I think actually before I leave, I forgot to finish this out. And so I will share my screen again on Zoom. And so I guess the main thing is the whole point of this lecture is I showed how is data stored in our RMG database? How do you add new data? The last thing is now that you've added it, how do you use it in your mechanism? Like how do you take advantage of those benefits? So for this, I'm looking at the input file for the minimal example, which I believe you ran yesterday. And so in the database block, you have your thermal libraries where you're specifying, which thermal libraries you want to add. So in this case, I really trust the values that I add. So I could add, the Speakerman thermal library example here, whatever that was. And then as far as how to get the new kinetic estimates, you could list the families here. So we could explicitly say, I want the Diels-Alder to be included. As it turns out, default points to this big list in RMG database, which you can find at this path, input, kinetics, families, and then recommended. And as we see, it already includes Diels-Alder. So it's just a shorthand notation for that. What that means is that new rate tree that we added and then, eventually push to GitHub, make a PR and incorporate, it will be used in here for everyone's new mechanism. So that's how you actually get the benefit of the new data. Yeah, modifying kinetics families and thermal libraries. So I think that covers everything that I wanted to go over. Feel free to find me later today if you have any follow-up questions, but we'll move on to the next portion of the workshop.